Thank you guys. Thank you very much. And I really do apologize for not being there physically. I know it kind of sucks to go to a conference and just see a guy on the screen. So I'm really sorry about that. And we'll do our best with this. Usually when I do conference talks, we have some audience interaction. So we'll see if it works out or not. I'm going to ask questions. We'll see if it works out. But generally, why are we even having this talk? This is not a data conference. It's a software developer conference. But the reason I think and what I want to do with this talk is all of the big data processing technologies we have today were written by software developers, and they were written for reasons of economics and technology and requirements of companies as they developed. And so there's no mystery, there's no some magical type of big data people who own all of this knowledge. It's just software developers like myself, like yourselves, who build all these tools. And so what I want to do with this talk is to figure out what were the requirements and the economic reasons for needing these tools? And if we had to build them ourselves today, how would we solve that? And is it similar to the way actual technologies evolved or not, right? And so before we do that, right, we need to talk about what is big data in the first place? What are we talking about? So there are a lot of things which fall under the category of big data, but the original problem that this whole set of technologies came to solve was that we needed some way to address data sets that were too large and complex for traditional data processing tools like relational databases that everyone, I presume, is familiar with. And which is why a whole set of very new and different set of tools came about within the last 20-ish years or so that are specifically optimized to work with very large amounts of data. The next talk after mine here actually talks about online processing. And that's a really cool talk because mine will actually lead into it nicely. And there are, of course, a lot of things around big data which we won't be able to cover here, like NoSQL databases and stream processing and a bunch of other stuff. But I think the core problem that we want to talk about is how did large data processing applications came to be, and how would we go about processing them, creating them? Now, before we can talk about which technologies exist to process and query large amounts of data, we need to figure out why would we even need that in the first place. And this is where I want to talk about what is called the data value chain, or the data value continuum. There's a really fascinating article by Scott Yar, who was the co-founder of VoltDB, one of the relational NoSQL databases, which talks about generally that the value of data is not constant. The value of data depends on the amount of it and the age of data. Now, intuitively, I think it's easy to understand for everybody who thinks of, let's say, what is the value of an individual data record, data item? It starts out usually very high because usually it's the online transactional applications or production applications which deal with individual data items. And over time, when we store this item, the value decays. The best example is if you think of, let's say you log onto a e-commerce website, and the commerce website needs to track your shopping cart as you go through the website. You add stuff to the shopping cart, you do things, eventually you go to the checkout, you click the checkout button, and this data item, which is stored in a database or a cache somewhere, is really important until you actually check out. And then eventually, when you finish your transaction and you close the website, the shopping cart stops being valuable. Its value drops off sharply. It's stored in some database forever somewhere. And eventually, when we accumulate enough of these records, enough shopping carts, for example, a year worth of records of all the people who bought anything, the value of data as an individual item drops, but the value of data in aggregate, a large amount of shopping cart records from a long history, goes up in value because we can now use it to analyze trends, create insights, train machine learning models, do all kinds of stuff. And so the value of large amounts of data increases with how much data you can store and process, and the look back, the time of you can actually look back and analyze trends over. And this explains why there are two distinct sets of technologies that exist to address each side of this graph. The traditional database applications that I'm sure most of you have worked with, SQL servers, your MongoDBs, Elasticsearches, the online databases, they're addressing the left side of the graph. They work with individual data items with high concurrency and very high throughput, and they're optimized to quickly retrieve and store in small numbers of items. And the other side of this chart is working with very large amounts of data. And that is a problem which isn't online. We don't need to pull up a terabyte worth of data for our application at runtime. But we do need, in hindsight, to analyze very large amounts of data not to mention store them, and do this cost effectively, right? Which is why there is a clear distinction between technologies of what's known as OLTP, online transaction processing databases, which are the traditional databases you're all familiar with, like SQL Server, Oracle, MongoDB, all of those, and OLAP databases, online analytical processing databases and data stores, which address the analytical side of things, which means working with a lot of data over long periods of time. And specifically in this talk, obviously, we're not going to be talking about OLTP because, well, you're familiar with them, and in my eyes, it's less interesting, but we are going to be talking about analytical data stores. Now, when it comes to analytics, this is a typical example of an analytical query. Now, over the past 20 years, most data processing technologies have kind of standardized on SQL as the language of choice for analyzing data. I'm pretty sure most of you are familiar. Let's try this audience interaction thing by remote. Everyone raise your hand if you know SQL more or less. Let's see if it works and if the video lag. Okay, awesome. Hey, interaction works. See, that's exactly what I expected. Most people learn it in university or on their first job, and this is the de facto language. There was for a period of about 10 years ago, there was a period of time where every technology tried to get creative and invent their own query language. We can still see remains of that today. For example, MongoDB famously created their JavaScript JSON-based language. Elasticsearch had their JSON-based interface for querying data. But over time, each technology, even if it didn't start with SQL as the default query language, kind of added SQL as well, because that's what people expect. People expect to be able to query all of their data through a language they actually know well. Now, if we look at this query, this is very typical of how analytical queries work. 90% of queries I've ever written are based on this template. We select something and we aggregate on it. We join a bunch of tables together, we subselect some criteria, and maybe we group by some criteria. Now, this query looks very simple, but actually what it does is it hides 4 unique engineering challenges in a single query. Each one of the parts that are highlighted in red is a separate, completely distinct, very difficult engineering problem to solve in the world of big data. Let's go through them. So count represents aggregations, count, sum, average, whatever it is. It's a very hard computational challenge because it requires either pre-computing the aggregation ahead of time or at runtime running over all of our data and computing the aggregation, which is very computationally expensive. It becomes even more expensive in a distributed environment where you have a distributed database, a distributed system where you need to do this individually at every node in your system and then somehow combine the aggregation results. Join is a very hard operation. There's a reason we spent the last 50 years in the world of relational databases optimizing join algorithms, because it's a very expensive thing to try and join multiple data sets computationally and in memory. And it's especially difficult, again, if your environment is distributed, if you have to join across multiple different data sets or even databases. This is a problem that 20 years ago, we were trying to solve even the basic ability to join data at all. Imagine that you were at a company 30 years ago, a large enterprise. Databases weren't just pieces of software you install on a typical PC. Databases for most companies were huge physical appliances, like a whole closet you buy from IBM and put it in your basement, right? And databases were expensive and they didn't talk to each other. Different vendors' databases didn't really want to make them cross-operable. And so joining across data sets is a unique challenge of its own. Sub-selecting, obviously selecting of a subquery is a very hard problem that you need to build for, create indexes, create different systems. And grouping is, again, grouping and shuffling data is a problem that's very expensive computationally, but also expensive in memory because you have to group data into buckets in memory, which is, again, even harder in a distributed environment. And so the past 30 or 40 years of data technologies, we spent trying to solve different combinations of these 4 problems. And every technology we'll talk about today attempts to solve some of these problems and optimizes for some, and then obviously makes trade-offs and doesn't optimize for others. And so the first one we want to talk about is data warehouses. Now, even if you're not familiar with data warehouses, it's very likely that you've used some data warehouse even today. The data warehouses back in the past, 20, 30 years ago, were, again, large pieces of software, probably appliances. Today, we've shifted most of this to the cloud. The modern data warehouses are things you can just use your credit card to buy from AWS or from Google Cloud or Azure. And it's likely that if your company has some kind of data portal where a developer can go in and explore their data and run queries on some analytical tables, on the back end, you're talking to some kind of data warehouse. But the idea for data warehouses was to solve 3 of the original problems we had in the query we saw just now. One is the ability to join data in the first place. The idea of a data warehouse is to have a central place that is not used for operational needs, but rather only used for data analytics. One of the biggest no-nos you can have in the world of databases is to let users run analytical queries on your production database. This is the first thing you learn not to do as a DBA, because analytical queries are very different from your online transactional queries, and they don't really share space very well in a single instance of a single database. You want to move your analytical queries to a separate system so that they don't actually collide with the runtime operational database. And so data warehouse was an attempt early on in the late 80s of the previous century to define a system which will collect data from all the different places in the company, move data from different individual databases into the central repository, central warehouse, where you can now join across different data sets where you couldn't before because they were in different databases. And you could schematize and manage this data centrally and store it for a long enough time if you attach enough storage, and then query it. And again, you don't query it in production, you query it by analytical users who are okay waiting a little bit for your query to complete. The trade-offs here, of course, are it's usually very slow and it's very expensive. Now, this isn't a problem that was just in the 80s. Even today, today is just as much of a problem to join across different data sets. The modern architectures with microservices and polyglot storage, which means using the right kind of database for the right kind of job, means that a lot of companies have multiple different types of database. Maybe your user database is backed by MongoDB, and your online product database is backed by Elasticsearch, and your payments and receipts are sitting in PostgreSQL, because each one does the job best. But now your analysts want to query all 3 of those data sets together, and you can't really do that effectively in the place where the data is. You need to take it out and bring it into a central repository where you can actually manage all of this data and store a long history and query all of it. Now, this paper is one of the first papers which presented this idea of a data warehouse, of taking all the data in an organization and putting it into dedicated hardware. And this is a very influential paper. It had many citations, which is, if you're not from academia, citations are like reposts or retweets, I guess, re-access, I think they would call them. So this created a lot of follow-up research in the world. Now, data warehouses solve one aspect of this problem, which is actually joining data and allowing users to run analytical queries. But there's another aspect, which is users are impatient. Nobody wants to wait many minutes for their analytical query to continue to complete, to get the result. And even more so, if you're trying to do something interactively, you want to try different things, run many queries at once, data warehouses don't really solve that. You can't really iterate very quickly on your research when you're trying to analyze data. And so a different technology came along a few years after data warehouses, which is called OLAP. Now, what we're going to do is we're going to do an exercise. Like, we're online, so we'll try to not do it too interactive, but let me tell you a story. Imagine that you're a software developer. It should be very easy for most of you because you probably are a software developer. And your manager or your boss, someone in your company comes to you and says, we have a sales database, which has all the sales the company does. I want you to write me an application, which when I click a button, will show me the sum of all the sales, just one number. All your application has to do is take all of the sales for the past month, sum them together, and show me the total number of sales. You say, okay, no problem, that should be easy. The only requirement we have is to do this in the least amount of time possible. How would we solve this, right? If I was there physically, we could actually talk about this, but I want you to at least think for a few seconds, how would you use whatever language of choice that you want to write a program which would actually do that, which would take data from a database and just present the sum as quickly as possible. I'll give you a couple of seconds to think about it. Because I've talked about this a lot, I'll tell you some of the most common answers people usually come up with. And I suspect most of you have thought of this. So the most straightforward thing we can do is just take all of this data in advance, load it into memory, compute the sum, and then store the sum as a single float value. And when we click the button, we show the value. We pre-compute, we pre-aggregate all of this data. Now, of course, it gets more complicated because a week after, your manager comes to you and says, that was a wonderful application. I love using it. It's so fast and responsive. But you know what's missing? I want to also see all of the sales per country. Can you please improve the application so it shows not just the sum of all the sales, but also sum of sales per country? You think to yourself, okay, well, how can we extend this original idea of pre-computing data to include this new dimension that we need to aggregate on, right? How do we do this per country? Now, most people, when you ask that, will say, okay, well, instead of storing one counter, one integer or float, let's store one for every country. There's give or take 200 countries in the world without getting too political. So we'll have a hash map or a dictionary where the country ID is the key and the value is the sum of sales for that country. And every time we sell a new thing, we'll go and update the country counter, and we'll also update the total sum because that's useful. And then whenever we click the button, it will show us a table of all the countries with the sales because it's already loaded in memory. It's super fast. And that's wonderful. And a week later, your manager comes to you, you know, I love your new application. It's even better than I expected. Can you also show it not just by country, but also by day of the week? And then can you also make it show it by product category? And also this, and also this, and also another other thing. And what we've just invented now is called an OLAP cube. And an OLAP cube is a data structure that solves the other set of problems we have with analytical data, which is how can we quickly run aggregations on a lot of data? Because in this case, we're not actually keeping the original data in memory, we're only keeping the computed aggregates, which are much smaller than the original data in most cases, right? And so this was an idea that was proposed by Edgar Cod and Sally in 1993. Again, a very important research paper that was that led to a bunch of different software systems being written. One of the most famous OLAP systems, OLAP cube systems that came about was by a company called Panorama Software, which Microsoft acquired in 1996. And this became Microsoft Analytical Services later on. That was one of the first systems I ever used. In 1999, I worked as a database programmer in Intel. And the biggest system I had to maintain was an OLAP cube, which computed all of the some combination of things which we needed internally. And every night, the system would run and compute the cube for the previous day's work or data. And every morning we would come into work and we would check whether the cube computation succeeded or not. And if it succeeded, which was about half the time, it was a very easy day. And if it didn't succeed, we would spend the day fixing whatever went wrong with computing the cube. And that kind of brings us to different trade-offs of OLAPs, right? So if you can imagine OLAP as a multidimensional Excel spreadsheet, right? If you think of it as, well, if an Excel spreadsheet is a two-dimensional table, and you can imagine it in 3D, right? Because there's some depth to it, and try to imagine it in 4D, which is a hypercube, or 5D, a tesseract, and however many dimensions you can fit in your mind. You can now take this multidimensional structure in memory and slice it along any pre-computed dimensions and get the aggregates for that dimension, right? So if you, in this example, if you want to see all of the sales of camping equipment in Northern Europe in 2005, we would need to find the specific cell, which is 2005 along one axis, camping equipment on the other axis, and Northern Europe on the third axis. And that gives us a pre-computed value, which you can retrieve and show very quickly. So this is wonderful for users. You can aggregate data very quickly. We don't even need a lot of storage to keep it because you can fit all of this data in memory. Now, the downside of OLAPs is, actually take a couple of seconds to think of what are some potential problems with this approach of trying to pre-compute all of these different dimensions and store all this data in memory in advance. We'll take a couple of seconds to think of it. I'm not going to ask you directly because it's going to be awkward, but I will tell you some of those and you can compare whether you thought of the things I'm going to mention or not. So the biggest problem with this, of course, is cardinality. What happens if there are a lot of unique values along some dimension? Imagine that one of these axes is the user ID in a system with 100 million users. So now you have to compute the number of aggregations of 100 million users multiplied by all the different countries, but all the different dates and so on, right? So if one of your dimensions has very high cardinality, very high number of unique values, this model breaks down. The actual aggregated data takes more raw storage than the raw data, original data. And so you're limited in the kind of dimensions you can actually analyze with OLAP. The other problem is something which I already mentioned, which is you have to pre-compute the cube ahead of time. So first of all, you're looking at stale data. Like if you compute your cube every 24 hours, you can't see the data from today. You can only see the data from yesterday and back. Today, modern OLAP databases can actually do this in more or less real time. So you're not limited to stale data. But of course, it comes at the cost of expense and more complexity and being harder to maintain. The other problem, of course, is what if I want to query on a dimension which isn't pre-computed? If I want to query camping equipment on Mondays, and we don't have a dimension which indexes days of the week, we can't do that. We're limited to the things we thought of in advance. And if you want to add a new dimension, we have to throw everything out and compute the cube from the start. So that is the downside of using OLAPs. Of course, modern systems usually don't limit themselves to one specific aspect. It's not just OLAP cubes or just warehouses. There are modern systems which combine aspects of both. This is typically what happens when we encounter a new software engineering problem. We first solve it for a narrow use case, and then we expand the amount of solutions we can fit into our software. And so today, systems like Apache Druid, Apache Pinot, which is the next talk after this one, ClickHouse, and a bunch of other softwares, they combine both traditional databases and data warehouses and OLAP solutions all in one place, which makes it easier. But of course, the trade-off is it's way more expensive and much more complex to maintain. Now, all of the solutions we talked about, they share both data warehouses and OLAPs, and most of these online analytical services, they share one big downside, which is they're very expensive. They're very expensive expensive way to store data in general. This is actually true about regular databases as well. And the reason they're expensive is that, first of all, you pay for ingesting data into your system upfront, right? You have to index all of this data. You have to manage it on disk. You have to spend the processing power on the actual database software to keep it running. And they're expensive because you continuously maintain them. Even if you don't query this data and you don't use it, you have to pay for your database server. You have to maintain it. You have to replace parts. So storing data, especially for analytics, in online systems is inherently more expensive. And the reason it's more expensive is because of something that is called dark data. Now, dark data has nothing to do with the dark web, if you thought of that. It's not data about drugs and guns. Dark data is a phenomenon that happens in pretty much all companies and all businesses in the industry, and that is data which is stored and collected, but not actually used for anything meaningful. It doesn't provide any value. And for most companies today, their ability to actually collect and store data exceeds the throughput at which they can actually make something useful out of this data, to analyze this data. This seems counterintuitive. Why would you store this data unless you've been a DBA for a while, in which case you know that nobody ever throws out data. It's very difficult to part with data and say, we don't need this and store this anymore. But depending on which research you look at, there's a research paper from IBM, which analyzed machine-generated data, and they estimate that between 60 and 90% of all data collected and stored is never used for anything valuable, meaningful, which seems incredible and incredibly wasteful. 90% of all data you ever stored is not useful, but I can give you an example that makes it very, very tangible. I'm sure everyone is familiar with application logs, right? I hope all of your applications have production logs to actually figure out what's going on in production. So think of what is logged by applications most of the time. Most logs are informational, right? They're, the system processed a transaction, or we stored something in a database successfully. Response code 200 OK. That's the vast majority of logs. I hope that's the vast majority of logs and not, errors everywhere. And a very small part of the logs are errors and information that you might want to see. In fact, in many systems, one of the systems I worked on in Proofpoint before I came to Meta, the most expensive data store was the logging cluster and not the production database. Because logs are ubiquitous, especially in microservice-driven systems. There are a lot of individual applications all writing application logs, and most logs are never actually useful because they're just statuses okay. In fact, you really need logs when something goes wrong, and you don't want to look at all the logs. You just want to look at the specific things that are interesting, like errors or specific subsets from one different service. And so 90%, more than 90% of logs are just stored. So if you store logs in an online system, which is things like Elasticsearch, the Elk cluster, or Splunk, or a bunch of other systems, which store logs in essentially a database, it's very expensive. You pay for indexing all the logs up front, and you keep paying for the database to be online, even if you don't actually query it or query a small subset of it. So this is the reason why in the early 2000s, most of the data world, the big data world, moved towards something called a data lake, which is a different way of storing data and a different way of querying data. This is also the reason why most modern logging solutions are moving away from this database management system towards things that are more like big data technologies. So to explain what a data lake is, let me ask you something, and we'll think about this exercise together. What is the cheapest and easiest way to store data in software and IT systems? Think about it for a second. I know I asked this question of a lot of people, and the most common answer is put it in a file. Files on a disk or on a shared system somewhere are by far the cheapest and simplest way to store a large amount of data. Now, what if we could actually put all of our data in files and query it there? We don't need to pay for an expensive database if we're not querying the data. It can just rest in a file. Storage is cheap. Today's storage is especially cheap. You can get 1 terabyte of storage on Amazon S3 costs $20 a month. Now, $20 is $20, right? But it's still relatively cheap for a whole terabyte of storage. But how do we, let's say we do that. We optimize for cost. We store data as cheaply as we can in a file. Okay, well, how do we query this data? In order to answer that, let's all now together build a new big data platform. And what we're going to do is we're going to solve the most well-known exercise in big data. You know how if you learn a new programming language, the first thing you do is you write a hello world program. So in data processing, the hello world program is what's called a word count. You write something which counts all the words in text in a large amount of data. So what we're going to do is now think of whatever programming language that you're comfortable with. How would you write a program which reads and counts all the word in a 1 terabyte file? It's a 1 terabyte file of plain English text, plain ASCII. All you have to do is read the file and output how many words there are. We'll take a few seconds to think about it, and then we'll talk about some of the most common ways of doing this. I hope you're just not looking at the screen, but actually thinking of how would you write this. But I'll spoil it for you, and I'll tell you that the most common answer, of course, is you write whatever language you want, and you open the file, you read data from it sequentially, maybe in buffers or 1 byte at a time, and then whenever you switch from an alphanumeric character to a white space or a punctuation character, you increment the counter by 1 because you just moved from one word to a break between words. And you go through the entire file and you count those, and eventually you know how many words there are in the file. So now that we have this application, how could we optimize this for runtime? How can we make this application run faster? What are the optimizations we can do to solve this big data problem as quickly as we can? We'll again take a second to think about this, and I'll tell you some of the ways we can do that. So it's actually a very difficult question to answer because there are surprisingly few ways to optimize this problem as I presented it. You have one instance of a computer, you have one hard drive. The thing that you can't actually skip any of the bytes. You have to read every byte in the file, because if you skip any bytes, that might be another word and you would be miscounting. And so really the only way people usually suggest is to parallelize it. Let's say we'll have a bunch of threads all reading from the file from different places in the file. But the problem with trying to parallelize reading from a file in a single machine, in a single computer with a single storage system, is that it doesn't matter how parallelize the reading, or how quickly you read it, you're always bottlenecked by the throughput of the storage system. If you're on a spinning disk, you're always going to be limited to about 150 megabytes per second. If you're on an SSD, you're going to be limited by, let's say, 500 megabytes per second or so. But that's the fastest you can read the file, and that determines how quickly you can run this program. There's usually more than enough CPU power on any computer to actually run the software, to actually do the count, because the program itself is very simple. So we're always bottlenecked on storage. And so the next suggestion is always, okay, well, let's just use more computers. Let's spread out the storage. And that is the core idea behind data lakes and most of the big data system that exists today, which is to spread out the storage, to parallelize not just compute, but also parallelize the bandwidth of the hard drives that we use. Now, the problem with that, of course, is that it's not easy to do that. You have to add an extra layer of complexity. Because now, let's say we have 1 terabyte file and we split it into 10 different machines. Now we have 10 files, each one of 100 gigabytes, right? So now we need to take our program and we need to run a copy of our program on each one of these 10 computers. And each one will produce a result. But that's not the right result. They will only count the words on that 1/10 of the file. Now we need to add an extra step of taking all the different results, bringing them back to one single place and computing the reduced result, right, to re-aggregate them. So now we need some way to manage not just running our software and distributing our files. We need to go and distribute the application which runs the big data job, our word count, and then aggregates the partial results. And that is exactly what the first data lake, the first big data system actually does, except obviously on a bigger and more complex scale. So if you thought more or less along the lines I explained, congratulations, you just invented big data again in 2023. So the first big data system was something called Hadoop. This was a system that came about thanks to 2 major white papers that Google published in 2003 and 2004. In 2003, Google published a white paper describing the Google file system, which is a distributed self-healing file system with redundancy built in. And that is what they use to store, the entire index of the entire internet and all the web scraping pages and so on. And a year later, they released a white paper describing a new algorithm that Google came up with called MapReduce, an algorithm for running distributed data computations across a large number of machines. And MapReduce is an algorithm that is exactly what we described. It has 2 steps, one step which maps data in a distributed way, and then another step, the reduce step, which takes partial results and re-aggregates them into a single authoritative final result. And so in roughly 2002, 2 engineers, Doug Cutting and Mike Caffarella, were working on something called the Apache Nutch project, which was a search engine they were trying to build at the time. Now, in 2002, their goal was to build a search engine which could index 1 billion pages, which was actually larger than the size of the entire internet at the time. Now, it doesn't sound like a lot today because, what's 1 billion pages? No big deal, right? But in 2002, 1 billion pages was an almost impossible task. When they estimated how much it would cost to actually solve that search engine with available tools at the time, with online databases and data warehouses, they came out with an estimate of roughly $500,000 and $50,000 maintenance per month, which was just impractical. And so instead, they used the new ideas that came out of the 2 Google white papers to create a new system called Hadoop, which is whose core idea is exactly what we described, which is to store data in plain files in a distributed file system, and then take the query you want to run, express the query you want to run as an application. In Hadoop, it was a Java application, and then build a mechanism which will just distribute the application to where the data is located. Instead of like a normal database, to bring your data to where your compute lives, you're actually sending your compute, your application, to where the data lives, running the processing there, and then bringing back the results to a single centralized place, which can actually produce the result. And this was a revolutionary idea, which kind of took over the entire world of offline data processing within a short amount of time. And even today, many of the follow-up systems that came out from Hadoop, obviously it was a very cumbersome system at the time, because instead of writing a nice query, you had to actually write a Java application that expresses the query you want to run on the data, which was great for software developers, but for nobody else at all. And so follow-up generations of the same idea adopted nice query languages, and these days cloud services where you don't even need to host the physical infrastructure. You just use cloud services to do the same thing. But in general, the core idea remains, which is we store data as efficiently as possible in files and then bring our application and our query to the data, right? Now, of course, if we just store them in files, exactly as we talked about in the word count example, there's very little optimizations you can do to avoid reading the entire file, right? Because you still have to read all of the data. And so the next generations of the same system, this core idea, tried borrowing ideas from standard databases and bringing those into the big data world, into the Hadoop world, which is, what if we don't store the data in just plain files? We don't need to write data as text. First of all, of course, we can compress the text, right? Because if you compress text, you save on that bandwidth and you have to read it. But compression is very straightforward, and of course, it doesn't solve the entire problem. You still have to decompress and process all of the data in your files. But what if we didn't have to? What if we actually could manipulate the data a little bit before we write it into a file? Not to the level that databases build indexes and maintain very complex in-memory structures, but we can manipulate it enough to optimize some types of queries. And this is what brought about the invention of columnar data formats, columnar file formats, which are ways to actually store data, again, in files, which is still very cheap on cheap storage. But because we organize the data in advance in the file, it lets us take advantage of certain properties of the file to query not the entire file, but rather a small subset of the file. So there are two popular formats called ORC, ORC, and Parquet. They're basically the same thing. They do the same thing. But the core idea is, as you're writing your file, you don't write data continuously into the file. You buffer a bunch of data. By default, all of them just take 10,000 records. And you compute various statistics on the data you're buffered. Then you write this data into the file, and you write a header, which, for example, for every column computes the minimum and maximum amounts and averages. And for text columns, it creates dictionaries of all the unique words in the text, so that when you want to query this data, you don't need to read all of the data in the file. You can go to the header. And for example, if you just want to find the count, you don't even need to actually read the data and count the words. You actually have a pre-computed count. And if you want to check if a specific value exists in the data, you don't need to read the entire data. You can just read the dictionary of unique words and see if the word exists in that dictionary. So it opens up space for a lot of different interesting optimizations, which avoid the biggest problem in this way of storing data, which is you don't need to read everything. You can optimize on bandwidth this way. The other way to optimize this is the reason columnar formats called columnar is because, unlike traditional databases and just plain files where you store the entire data record sequentially on disk, columnar formats break each record into individual columns and store columns sequentially on disk. So let's say you're storing users, right? And users have a first name, a last name, an age, and I don't know, date of birth. And so instead of storing first name, last name, age, date of birth sequentially in a file, you would have one entire region of the file with just first names, and then after that, the entire column of last names, and then ages, and so on, because we're optimizing for analytical queries. And usually when you want to do analytical queries, let's say you want to find the average age of all the users in your users' data. So you would only need to read the age column. You don't need to read all the other columns. And you can do that very efficiently because you go to the right place in the file where the age column starts. You read the entire column sequentially, which is, again, very efficient, especially on spinning disks. And then you don't read any of the other data in the file, which is, again, a huge improvement. And so this is the core idea of actually trading some of the nice features we get from data warehouses and OLAPs, which are very expensive, to something that's much cheaper, obviously not as efficient and not as quick, because when you run these Hadoop style queries, and today's you wouldn't use Hadoop. You would not find Hadoop except if you're in a bank or like a big insurance company. But the next generation of tools like Apache Presto and Apache Spark, they work along the same principles. Today you can do this relatively quickly. It wouldn't be as quickly as querying a database, but still in interactive user time, and it's significantly cheaper. And there's a good reason why all of these technologies appeared more or less within the same span of 2 or 3 years. Hadoop came out in 2002, but the technologies that persisted to this day, which are still used today, all came out between 2010 and 2012. Spark showed up in 2010 or so. Hive query, BigQuery, which is what Google used for their big data, Dremel, which is an open source implementation of BigQuery, Apache Drill, Presto, which is basically the same thing, but written for Facebook. They all had their first releases within the span of years. And there's a bunch of economic and technical reasons for that. Economic is because this is where the internet really took off. The advent of user analytics and ad tech and social networks kind of peaked around 2010, and the technical requirements became very, very much larger than before. You had to process a lot more data. You had to do it interactively. You had a lot more need for interactive analytics of data. Companies like Google and Facebook have actually exposed this analytical data to their users, right? If you're running ads on Google or you're running ads on Facebook, for example, as a user, as someone who's advertising, you have access to all of these tools through some interface. When you go and you check how your ad campaign is doing, in the background somewhere, a Presto query runs on a bunch of big data systems, right? And so that was why within a very few short years, all these companies had to either invent or adopt very similar tools which worked on similar principles by trading off cost for efficiency. Now, in these days, in modern days, right, you're not going to go and install Hadoop on a system. Most systems are what we call the third generation big data tools today, which systems that combine aspects of both warehouses and OLAPs and data lakes into one system. And if you're building a data architecture today, you wouldn't go directly to a data lake. You would usually use third generation cloud-based systems, which provide all of this as a service, right? And so these days, there's a thing called the data lakehouse, which is, again, exactly as it sounds, is a system which combines different aspects of both data warehouses where they can store a lot of data in a way that's schematized and well-structured from different systems, and have the option of building OLAP cubes on top of it, and also store it in plain file formats in the data lake sense to reduce costs. And so this is a trade-off, which again trades complexity for the ability to do all of these things at once. And those are roughly the three main big data tools we have today, and all of them still exist. And even if you're not like a big data geek like me, it's very likely that your company is using some combination of those, and you will find yourself at least accessing them as users throughout your work sometime. All of them have different trade-offs and different levels of guarantees they provide. But in general, these days, this is going to be the domain of data lakehouses, which combine kind of all of those together. Now we're coming to the end of our talk. I'm going to look and see if there are any questions, which I'll be happy to answer. And if not, you can also find me on LinkedIn or anywhere else and ask me data questions as much as you like. So thank you very much for listening. If we find any questions, I'll be happy to answer them.